Alright, so there are plenty of times in life when u substitution just won't solve your integral. And often when that's the case, it's a good idea to try the next thing, which is integration by parts, IBP. So what do you need to know in order to do integration by parts? The answer is, first you need to know about the product rule for derivatives. So that's if you have a u times a v and you take the derivative, then the result is a u prime v plus a u times a v prime. Okay. And that's the way we usually know and love this product rule. But for the purpose of integration by parts, it's really convenient to rearrange the product rule. So we'll end up with a rearranged product rule, which looks like this. U times v prime is equal to the derivative of uv minus u prime times v. I think you can follow that algebra, how you get from one to the other. So this is a non-standard form, but that's the form of the product rule that we'll use today. And finally, the other thing that you need to know before using integration by parts is this fundamental theorem of calculus. And I'll write it down in a kind of a funny form. If you go from a to b, and you're dealing with the derivative of some stuff, then the result is this stuff evaluated at b minus the stuff evaluated at a. What if the stuff has a special form, u times v? Then you would have u of b times v of b minus u of a, v of a. Is that a fair statement? So integral of a derivative is just the original function back again. That's what you need in order to do integration by parts. Alright, now let's do it in general. So this is a more theoretical version of integration by parts. So the most general integral you can come up with is an integral from a to b of some stuff with respect to x. So if you want to integrate by parts, the first step is to find a u and a v, so that, or we can even say find a u and a v prime, so that stuff is the same as a u times a v prime. Then you also want to find u prime, and you want to find v. So once you've decided what u is, it's easy to define u prime. But finding v from v prime is itself an antiderivative problem, and that can sometimes be hard. But in any case, let's assume that we've decided what u and v prime are. That's a choice. And then we found u prime and v. The next step is to use the reverse product rule, or the rearranged product rule, to change the integral into the derivative of the product uv, that's from a to b with respect to x, and then we'll have to subtract integral from a to b of the other way. So we'll have the derivative will hop from the v to the u in effect, so we'll have a u prime times a v dx. So we started with some integral, and now we have two new ones. This first one is super easy though, that's just fundamental theorem of calculus. So it's this stuff at b minus that stuff at a. So it's u of b, v of b, minus u of a, v of a. That was this first integral. And then we better subtract this new integral. So that's from a to b of u prime times v dx. So you'll notice that we haven't really solved an integral here yet. We started with one integral, now we have a different one we have to work out. And it might be true that this new integral is even more difficult than the one we started with, in which case we've gone down a path that wasn't very helpful. So integration by parts isn't really, properly speaking, a way of solving integrals, it's a way of replacing integrals with other integrals. And it's only useful if the new integral is easier than the old one. So in the end, the formula that people remember is an integral of u times v prime is equal to u times v minus integral of u v prime. This is the indefinite version. So you can see here, in this integral, the derivative has hopped from the v, whoops, to the u. Okay, so for our first example, we're going to consider an integration by parts problem, integral from 0 to 1 of x times the cosine of pi x dx. And so in integration by parts, the first step is to split the integrand up into two chunks, which we'll call u and v prime. So we'll say u equals some of that, and v prime equals another part of that. And it's up to us to choose which parts of the integrand to put into u and which parts to put into v prime. Later on, we're going to need a u prime and a v. So whatever we put here, we're going to end up differentiating. Whatever we put here, we're going to end up anti-differentiating. So that's how you make the choice. You want the things on the bottom to end up being very simple, as we'll see later on. So I'm going to stick the x in here for u, and I'm going to stick the rest of that, cosine of the pi x, in for v prime, on the grounds that when you differentiate u, you get just 1, which is simpler and nicer than x. I'd rather have a problem with the 1 in it. And when you anti-differentiate the v prime, you end up with, I guess, a sine of pi x, and then we better divide by pi. I think if I differentiate this using the chain rule, we'll get that back. So this at least is basically no worse than that was. So now that we've written our integrand as u times a v prime, we can transform the original problem into integral of the derivative of the product of u and v minus, then we have u prime times v. That's the rearranged product rule that we've just used inside the integrand. So then let's write that into two chunks, and that's again from 0 to 1, I guess. Okay, so the first thing, we have an integral of a derivative. So you can just plug in the 1 and 0 into the product u times v. So if I put in a 1, here we have a 1, here we have sine of pi, that's a 0, I think. And then let's look at plugging in a 0. If we put in a 0 here, you get nothing. Okay, so that's interesting. We got nothing from that first chunk. And then we're subtracting off now the integral of u prime, which was 1, times v, which was this 1 over pi sine of pi x. And that's from 0 to 1. So then we have an integral of minus sine. So that's, the integral of sine is going to become a minus cosine, so the minus will cancel. We'll end up with positive 1 over pi. And then there's another factor of 1 over pi from this integral. And then we have cosine of pi times x. And then we're evaluating at 1 and at 0. Okay, if we stick in a 1, then you have cosine of pi. Cosine of pi is negative 1, so you have minus 1 over pi squared. If you put in a 0, you have cosine of 0, that's 1. So minus, again, 1 over pi squared. So this is negative 2 over pi squared. Okay, so let's think for a second. Does this make sense? Should our answer be negative? I think it does, because cosine looks like this, right? From 0 to pi. And then, but this factor of x will squash it in the first part and squash it less in the second part, because x is small in the first part, x is big in the second part. So I think it makes sense that we'll have a small positive area, a larger negative area. It makes sense we should have a negative answer. Okay, so that's one example. Alright, so let's look at a second example. We're going to look at the integral from 0 to 2 of the function t times e raised to the power 3t. So the first step in integration by parts is to take the integrand and split it up into two factors. We'll call one of them u, we'll call one of them v prime. And the idea is that the stuff you put in u should be easy, or have a nice derivative. And the stuff you put in v prime should have a nice or easy antiderivative. So if I look at this, so I can put t in either place, I guess, because t has an easy derivative. The derivative of t with respect to t is 1. If I put the t here, its integral isn't hard, but the result is a t squared over 2. And that would lead me to a problem that's worse than the one I started with. So I think we should put the t here. What about the v prime? Let's put e to the 3t in there, because the antiderivative of that at least won't be worse, really, than what we started with. It'll have a factor of 1/3, but that doesn't really matter. So since we've decided to put the t in this u and the e to the 3t in the v prime, then we have to work out what are u prime and v. U prime is easy, that's just 1. And v is an antiderivative of e to the 3t. If I think about that for a minute, I'll realize it's 1/3 e to the 3t. Because sure, if I take the derivative of this, I would use the chain rule and I'd multiply by the derivative of the top. So the 3 would cancel the 1/3, there we go. So okay, well, I'm happy. We've got our u of v prime, a u prime and a v. We're ready to transform the integral. So let's write it then as an integral from 0 to 2, and then let's put in here the derivative of u times v. I'm thinking about that rearranged product rule there. So we'll have a t times a 1/3 e to the 3t, derivative of that thing. So that's going to be the super easy integral of a derivative. And then in the rearranged product rule there's a minus, and then we started out with a uv prime, so there's going to be a u prime times v, and u prime was -1, v is that stuff, so this integral works out to be a 1/3 e to the 3t dt. So then let's see what we can do here. This first integral, like I said, is easy using the fundamental theorem of calculus. So we just need to plug in 2's and 0's to these things and subtract. If I put in a 2, I guess I get 2/3 e to the 6t. Whoops, just e to the 6, right? There we go. And if I put in a 0, I get 0. So there's nothing else there. Then let's think about this integral. It'll be -1/3. And then what's the antiderivative of e to the 3t? That's another 1/3 times e to the 3t. So let's write that, and then we'll evaluate at 2 and evaluate at 0. Okay, so we're making progress here. This is going to be 2/3 e to the 6 minus, so this is 1/9 e raised to the power 6. And then plus, I guess, 1/9. Is that a fair statement? So finally then we'll have 2/3 minus 1/9. That's 6/9 minus 1/9. So it's 5/9 e raised to the power 6 minus plus 1/9. I think we got it. Great.
Don't be fooled by the logs that it's got, for this IBP is the right thought. Try new substitution, but that further tangles the knot. Don't think that you don't know how to solve it.
Alright, so now we're ready to go. Let's see what we can do. So the first step, we've got an integrand here that we have to split up into two factors, one of which we'll call u and the other we will call v prime. And we will need, later, u prime, and we'll need v. So whatever we stick in here, we're going to end up differentiating. Whatever we stick in here, we will end up anti-differentiating. So we have to choose carefully. So this root t, let's see, I could either differentiate that or I could anti-differentiate that. I know how to do both of those things. What about the natural log? I know how to differentiate that, but I'm not really sure how to anti-differentiate that. So I think I better stick the natural log in the u. And then this thing I'll dump into the v prime. So I'll call that t to the 1/2. Okay, and once we've made those decisions, then we just write down the derivative of natural log. That's 1 over t. And then the antiderivative of t to the 1/2, that's t. I know the power will go up by 1, so it's t to the 3/2. And so I need a constant here, because if I differentiate this, I would bring down the 3/2, but there isn't a constant there, so I need a 2/3 here, so that they'll cancel. Okay, so now we've got our u and our v prime, and our u prime and our v worked out. So let's continue with this problem. The first thing we'll see is an integral of a derivative, and we've gotten some practice with that now, so let's just do it without writing that integral down. It's going to be u times v evaluated at 4 and 1. So that'll be natural log 4 times 2/3 times 4 to the 3/2 minus natural log of 1. Ooh, natural log of 1 is 0. So that's all there is. Okay, and then we need to subtract another integral, which will go from 1 to 4, just like the first. And this one was a u times a v prime that we started out with. So in the end, we're going to have a u prime times a v, which we can write as 2/3 times t to the power, here's some algebra, t to the power 1/2 dt. So was our integration by parts a success? Is the new integral easier to do than the old one? I would say definitely yes. So let's write this out here in a simplified version. Let's see if we do 4 raised to the power 3/2. I think we'll get 8, so that's 16/3 times natural log of 4. And then here we'll have minus, the t will become a t to the 3/2. We've seen this before, so then we'll need a 4/9 on it. And then this whole thing will evaluate at 4 and at 1. So let's write that down, 16/3 natural log 4 minus, okay, so if we had a 4 here, that would be 4 times 8 is 32 over 9 plus 4/9. I think that's it. So then we'll have 16/3 times natural log 4, and then here what do we get? Minus 28/9. Great. Alright, so we've just got 3 examples. In class we're going to do a couple more basic examples, make sure we're all on the same page. And then you'll have a choice of exploring 4 fancy versions of integration by parts. So the first one here is an integral which you can solve by integrating by parts twice. And it's a dramatic moment because you feel like you've gotten back to where you started and all of your work was wasted. But in fact, you've nearly solved the problem. It's very dramatic. Another one is a problem like this, which you can solve after integrating by parts 5 different times. And there's a cute method that helps you keep track of those many integrations all at once. One of the options is a fancy version, meaning a multi-dimensional version of integration by parts, where you'll see these triangles essentially are derivatives. So in some sense, a triangle has hopped from the v to the u. There were 2 of them here, but later they each have 1. And then finally, you can use, oddly enough, integration by parts to give a surprising answer to the question, what should we say is 3.5 factorial? You can remember we've already seen that 4 factorial is 24, but what's 3.5 factorial? That's a very exciting thing.